Welcome to a new phase of the Marble Machine project. I have this CAD model of a machine that I know I can make work and I know I want to build. So now I'm ready to actually design this machine. The reason that I'm seeing this as a new phase of the project is that I'm going to make these technical videos with design requirements and stuff. And these videos are going to be a little bit tougher for some people, and that's why I'm extra happy that we have 25 new backers this week. So thank you so much for supporting kind of when this project goes into its most theoretical phase. With your amazing support, I feel I can focus on what I should do to finish this project rather than trying to get a lot of YouTube views. So all the nerds and engineers who are actually into this process, you are my true heroes. Thank you, it means so much. I want to start by designing the drivetrain of the machine, all the shafts and all the wheels. Previously, when I've built stuff, I've just started building, but I can't do that if I want to succeed with this machine. I need to be more deliberate with the process. So I'm going to start by writing down some requirements for the drivetrain of this design. We're going to start by asking, what should the drivetrain do? The drivetrain should be powered by 1 to 4 humans. The drivetrain should be able to convert an uneven power input into an even RPM. The drivetrain should be aesthetically mesmerizing, be silent, efficient, easy to disassemble for transport. Words like easy is called weak words in design requirements. Those are not well defined. So let's say a 4-person crew should be able to disassemble the machine in 2 hours. So now we can remove the easy to disassemble. Okay, so now we have 7 drivetrain requirements that is design agnostic, what it should do. And now I'm going to jump into a little bit more how it should do that. Okay, so here's some detailed requirements about the main flywheel. So what I'm going to do now is that I'm going to make a placeholder CAD file according to all these design requirements. And then I can make a circular pattern with 6 instances. Okay, we have our first part. We have the flywheel. Let's make a couple of more. The Huygens drive. The weight should have an adjustable range between X to X kilo. The first thing that happens in the drivetrain is that these 4 pedals get pressed by the operators. And the force from the pedals should go into this ratchet wheel of the Huygens drive. And I haven't figured out how yet. So I think the next step for me is going to be to do a bit of a brainstorm around how to connect the pedal force to this shaft. The pedals should be ergonomic. I'm facing a very interesting choice here. Either the pedals should be like this, or the pedal should go straight up and down. So if we make a normal pedal like this is what I usually done. You can see that the surface is leaning down and up for the operator. But then I realized perhaps we can use this parallel mechanism like an X like this. The surface will be parallel, which will be very ergonomic for the operators. 10 centimeter step here is 10 degrees. When we push down this surface with our feet, we then want the pedal to rise by itself, and we can add a spring, for example, down here like this. So now I need to connect this wheel with this wheel. Paint is black. I'm not designing, I'm like sketching to figure out how everything needs to go together. Actually very happy about this parallel pedal solution. This makes a lot of sense, actually. Spring loaded, low noise. So here's something interesting. When we take the driven wheel and connect it to the large flywheel, what gear ratio should we have? We don't know, but we know we're going to have one. So I can put here, the gear ratio should be X. Let's add the Conveyor flywheel. It's the green smaller flywheel that you see in the exploded powertrain sketch. The Conveyor flywheel is connected to the ratchet shaft with a gear ratio of X. Here's the placeholder flywheel. We start to get this clock feeling when all the wheels are on top of each other. Now comes something interesting. The first 90-degree angled shaft here. So then is the question how we go from this shaft, which is rotating, to this shaft. We can use some kind of gearbox. So to angle this shaft, I would use something like this, like a double universal joint. So I'm making some simple conveyor rollers here. Boom. Ta-da! It starts to look like a robot. So the cool thing with the conveyor belts is that the varying load of the conveyor belts is not affecting this huge flywheel at all. And we did it like that because it says in the design requirements the drivetrain should be able to handle varying loads without an increase in music BPM deviation. That is one of the aspects of this drivetrain that I'm really, really happy about. It shouldn't matter for the music tempo if the marbles are in the conveyor belt or not. I do have to pump harder when the marbles are in the conveyor belt, but yeah. So we finalized the green part of the drivetrain here, the conveyor part of the drivetrain. But now we're going to make the red part, the music drivetrain, with the governor and the gearbox. Here's a mock-up Flyball governor that I made. Raise it up into the sky. Oh, that's beautiful! That is so cool. But how do we power this? There's a lot of different ways of achieving a 90-degree rotation shift. Look at this almond coupling. That is so space efficient. It's beautiful. I don't think we should use that for the high RPM though. I chose to power the Flyball governor in another way. So I'm just using this timing belt here and I'm twisting the belt around like this. And we have this idler, which is also a belt tensioner. I also realized that I have been lucky with the rotational direction of everything. The driven wheel here is rotating clockwise, which means that a huge flywheel is rotating clockwise, which feels right, like forward in time. But then this flywheel, the conveyor belt flywheel, is connected with this, which is rotating counterclockwise. So these wheels will rotate the other way around, which I think will create a nice clock feeling. So now we're done with the conveyor belts. Now let's do the music drivetrain. So we need to put a gearbox. What I just realized is that we can put the gearbox down from this angle so we can really see it from the front. So here's the gear train, and from this side you would see the chain swapping over left and right. We can see it in its full glory. That looks cool. I mean, there will be a lot of things in the way for this from the front. We will be standing there, there will be music instruments and stuff, but at least you have a chance to see it. So here's what I mean with the gearbox not going to be easy to be seen later. Where is it? Where is it? Where is it? There. So that's a bit of a shame. It would be nice to have kind of the gearbox fully visible. I remove that. We have the this is a bit of a shame. This is a bit of a shame. I kind of want the audience to see this, you know. I'm being so happy sitting designing all this, and then when we put the control station in front, I mean, it's cool on cool. It's ketchup with ice cream. It's two good things together. You'll still have the movement. It's more like a cool mechanical wall behind us. It's going to be crazy cool, and from certain angles you will see the machinery. In the best of worlds, there would be nothing in front of the mechanics. What if we would move all the control action to the sides of the machines to celebrate physics here in the middle? I don't want to design and haul around like 2,000 kilo of beautiful mechanics to hide them like this. I want them super visible. I almost want them like this. You of course wouldn't have the same cool camera angle like filming the operators from the side compared to when we put them in the middle. You have this amazing visuals with the main flywheel. Something to ponder, but not for now. I really want to show the mechanics. I think that's part of this artwork, and it feels like I'm putting two cool things in front of each other here. I get a feeling we might be able to do better than this. Perhaps... Oh, wait. We moved the control station. I'm copying the entire drivetrain. Boom! Let's put the mechanics as the superstar. You can still play guitar solo like in front of all the mechanics like this. There's some... Like, imagine being to this concert and you have full view of the mechanicals. I just have to solve that somehow. I just have to. never mind. Let's finish the drivetrain. I have this shaft here going out to the programming wheel, but now I need to decide if I should use a gear or a timing belt. And right now I'm going to decide because of rotational direction. So let's think about which way this shaft is rotating. This miter gear is clockwise, which means that this is counterclockwise. 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 I think we're super lucky. This means we can make a timing belt because I want this wheel to rotate counterclockwise. We're done. We are done. We have actually manifested the whole gear train. There's a lot of things missing. Safety brakes, torque limiters, control of the resistance of the flyball governor. This is just like the lowest resolution, but it's still our best maximum virtual product that we have currently. This is this week's new generations. So at the end here, I've been slacking a bit with filling in the design requirements and working from those. I'm just trying to learn to work with design requirements, and I'm slowly getting it. I'm also understanding that I have a lot to learn on how to use the design requirements. But anyway, thanks everyone for supporting this project, especially now when I need to make these more pragmatic videos of what I'm actually doing. A lot of people will tune out from this process, and you that are here now, you are the real support for the Marble Machine 3. Thanks for watching. See you next week. Hit me with your best shot.